If you think of a loom like it's a living thing, then the beat-up motion, that's its heartbeat. It's this steady, powerful pulse that literally pushes threads together, giving fabric its life, its strength, its whole structure. So let's unpack this crucial motion.
I mean, how do you go from just a bunch of loose threads to a solid, durable piece of cloth? What's the secret? Well, it's not just the threads themselves. It's all about a relentless, perfectly timed push. A mechanical push that happens over and over and over again.
All right, so here's what we're going to cover. We'll start with what this crucial push actually is, then we'll look at the basic machine that does the work and how it gets beefed up for heavy-duty stuff. From there, we'll get into the physics of tuning this whole thing, see what happens when you push it too far, and finally, wrap it all up to see how it engineers the fabrics we use every day.
Okay, first things first, let's get a clear definition. What exactly is the beat-up?
So in weaving, you've got three main things that have to happen. The beat-up is the third one. Just picture it. A new thread, that's called the weft, has just been shot through all the vertical threads. The beat-up is the action of this big, comb-like tool, called a reed, coming forward and bam! It forcefully pushes that new thread right into the main body of the fabric. So this motion really has two big jobs to do. First, it has to get that new thread exactly where it needs to go, nice and snug against all the others. And second, it compacts everything, making sure the spacing is perfectly even. That's what gives you a dense, stable piece of cloth instead of, a flimsy net.
All right, so now that we know what it is, let's look at the machine that makes it happen. For most fabrics, it's actually a pretty simple and honestly a beautiful piece of engineering.
And here it is. This is the absolute workhorse of the weaving world, a simple system driven by a crank. The key parts to see here are the rotating crankshaft, that connecting arm, and the sleigh. That's the big swinging frame that holds the reed, the comb part, and does all the pushing.
The whole sequence is super straightforward. The main shaft turns, which pushes the crank arm forward. That push makes the whole sleigh assembly swing towards the fabric. Then the reed, which is mounted on the sleigh, makes contact with that new thread, and wham! It beats it into place. Simple, right? One rotation, one beat. So effective.
But what happens if you're not making a light cotton shirt? What if you need to weave something incredibly dense, something really tough, like a heavy canvas or fabric for a tarp?
Yeah, for those kinds of super heavy industrial strength fabrics, that one single push just isn't gonna cut it. It doesn't have enough oomph to pack the threads tightly enough. The resistance is just too high. So, what's the solution? Well, you hit it twice.
And this is how they do it. This is the double beat-up mechanism. The absolute key here is this clever system of levers called a knuckle joint. You can see how it's designed to bend and then straighten out, and that's the whole secret to its power.
So how does this thing work? Well, as the main crankshaft makes just one single turn, its motion actually forces that knuckle joint to snap straight twice. And every single time it snaps straight, it delivers a really powerful beat-up. What this means is for every single new thread that gets put in, you're getting two heavy-duty pushes. That ensures that even the thickest, toughest yarns get packed in super tight. Okay, so whether it's one beat or two, the quality of the fabric really comes down to fine-tuning this whole motion. And this is where we get into some of the real engineering with something called the slutty eccentricity ratio. Just think of it like the master tuning knob on the loom.
The SOR, or just E for short, is a really simple but incredibly important ratio. It's just the radius of the crank divided by the length of the connecting arm. That's it. But that one little number completely dictates how the sleigh moves back and forth, how fast it goes, how hard it hits, and how long it pauses.
And this diagram really shows you that relationship in action. It's all about the ratio between R, the crank's radius, and L, the arm's length. If you change either of those, you fundamentally change the personality of the beat-up. You can make it either quick and sharp, or you can make it long and smooth.
And this brings us to a classic engineering trade-off, right? If you have a high SER, which you get with a shorter connecting arm, you get a much more aggressive beat-up. The sleigh moves faster, it hits harder, which is great for high-speed production in dense fabrics. But that jerky motion puts a ton of stress on the entire machine. It needs to be built tougher, which means it's more expensive. On the other hand, a low SER is much smoother, it's gentler on the loom, but it's just not as powerful.
This graph shows you exactly what that feels like from the machine's perspective. See the dotted line? That's a high SER. Look at how sharp that peak velocity is. That's a violent, jerky motion. The other lines,
They show lower ratios, and you can see the curve is much smoother, much gentler. The shape of this curve is everything. It determines the force of the beat up.
And this table just brings it all back down to earth. It connects the math directly to the kind of fabric you're making. A long connecting rod, that gives you a low SER, a smooth motion that's perfect for delicate stuff like silk. A short rod, that's a high SER, a jerky, high-force motion that you absolutely need for heavy wools and tough cottons. But what happens when you push that force too far? I mean, there's a limit to how hard you can slam that whiff thread into place. And when you go past that limit, well, the loom will definitely let you know. Yeah, there's a name for this problem. It's called bumping. And when you hear that loud bumping sound, it's a huge warning sign. It basically means the fabric has jammed up and the whole weaving process is starting to fail. So bumping is a very specific physical thing. It happens when the beat up is just so powerful that it shoves the cloth forward faster than the warp threads can keep up. For just a split second, all the tension in the fabric just disappears. It goes completely slack, and then it snaps taut again, and that's what makes that loud, harsh noise. These graphs show you exactly what's going on. The dashed line is the tension in the cloth. In the top graph, that's normal weaving, you can see the tension dips, but it always stays positive. It stays above zero. Now look at the bottom graph. When you get bumping, the force is so intense that the tension drops all the way to zero. You see how the peak of that force curve gets literally chopped off? And the irony is, this actually makes the beat up less effective, not more.
So when you put all these different pieces together, you start to realize that weaving isn't just an art form, it's this incredible exercise in balancing some really powerful forces.
Think about it. The choice between a gentle, single beat-up for silk or a powerful, double beat-up for industrial blankets. Tuning that Skinnerly eccentricity ratio to be smooth or aggressive. Making sure you have enough force, but not so much that you get bumping. Every single one of those is a carefully balanced engineering decision. And it's that balance that gives every fabric its unique character. From the softest silks to the toughest canvas, every single thread has been beaten into place by a precisely engineered force. It's the hidden heartbeat, giving every fabric its shape and its job. So the next time you feel a piece of fabric, maybe you'll think about the physics of that push, that heartbeat, that brought it all together.